Hello, this is the Platonic Academy of Melbourne, 2025, autumn 2025, and my name is Bernie Lewin, and this is a response to a request from some students to record our slides from Platonic Esoteric Geometry Part 2. And I thought rather than just recording the slides or putting up the slides that I might just talk through them. So this is what I'm doing now. I just made a recording for the discussion we had of music, but also in the class there was an introduction to tessellation. So we've been looking at working in the square, and working with triangles and working with hexagons. And in part one, we briefly introduced the pentagram and the pentagon, the very special geometric ratios involved there, the golden ratio, and and we will get to the pentagon and pentagram soon, the five-sided figure and the five-pointed star. But today we're mostly going to look at squares, triangles, and hexagons. So I will start the share screen now. Won't be a moment. Okay. Okay. So, tessellation. So we're talking here about, so we've made squares and we've played around with squares, squares in circles, and working with five-pointed stars and 10-pointed stars and so on, all based around the square. And here we want to just look at what's going on when you have tessellation, as in tiling of these sorts of shapes. So here's just a basic grid for the tessellation in the square. Here's a basic grid for the tessellation in the triangle. And notice how with the triangle that there's also the hexagon. So the hexagon is related to, the six-sided figure is related to the triangle tessellations. Those two are related. And now let's look at circles packing. Circles packing in a square, if you like. Let me see if I can get that up there. So this is what we would say circles packing in a square form, not how you'd normally see at the market with the oranges, but in a square form in this kind of grid. And notice that there are gaps, significant gaps in between the circles. And then you compare that to hexagon packing uh, in the, yeah, where, if you like, the oranges fall into the gaps and are packed more solidly, and you get less space between them. It's not uh, complete tessellation without any gaps, but it's a more solid and a more compact form. You can see the triangle in there, and you can see the hexagon in there. Okay, and here's proper hexagon packing as you get with the beehive. So you can see at various different levels, you can draw a hexagon on the various different scales, as you can in the other diagrams with squares and with triangles. They scale up and scale down, as we did in class, where we drew a larger form and then had smaller forms of the same type within. Okay, and this is a bit of a trick here. This is quite well known, quite common Roman tiling that sometimes even when you come across this at ancient sites, there is this amazing 3D sort of form coming through, even though the tiles might have been done, 1 or 2,000 years ago. And so the question is here, what form are we getting here? Is it triangles, squares, or hexagons? Well, it certainly looks like squares, but as we can see, it's actually based in hexagons. Okay, so another interesting question is looking at solids and the shapes on solids. Now, people might know that there's the Platonic solids, which are uniform in terms of having sides that are the same um, uh, uh, plane shapes. So with what do we say, even edges, edges that are the same. So we've got the pentagon as the sides of the 12-sided dodecahedron. And because it is the pentagon, the 5-sided figure, which expresses the golden ratios, as we saw in part 1, it was for in Plato's time, it was sacred and secret. And so when Plato in the Timaeus goes through the Platonic solids, he just obliquely refers to this one. But now think about this, an interesting thing in terms of tessellation. So we've got that there. Now we think, okay, how are you going to make a sphere, tessellate on a sphere? What would you use? Well, you think you might use pentagons, right? Because it's pretty much almost a sphere. Um, but in fact, when you tessellate on a sphere, it's not quite a sphere, right? It's pushed out, and so what works is this mixture of hexagons and pentagons, and they tessellate perfectly on a sphere. And you'll still see this on soccer balls. It was absolutely necessary when soccer balls were made from leather patches to use this design, but you will see other designs now. So it's is this, yeah, this is it here, the geometry of it. Okay, and in tessellation you will also find tessellation without any gaps using various different shapes. Here, the the basic geometry, the elementary geometry that's going on here is the hexagon. It's all done in the hexagon, but you see how you can, in that geometry, you can pull out squares and triangles, but you can see the hexagon as the basis for this tiling. And you might go around, people in Melbourne might go walk through Carlton and look at the tessellation in the terrace houses on their porches. There's various designs that use, or I don't know, in Europe, in Spain and in Islamic countries, you'll see tessellation that is quite complicated and uses various different basic shapes. But as geometry students here, what you've got to do, as with the rose windows in the cathedrals, look at them and see what is the elementary shape that's being used in the tessellation. Okay, so here is a design for tessellation, a basic design. You can imagine using this for textiles or for ceramic design. And here we've got the what do we got here? Well, we've got the square. It's basic. We've got a square here, right? And we've also got a hexagon working on. So squares and hexagons can go together. And here we can see the hexagon scaling up. Okay, and over here it's a lot more complicated with pentagons, and that's why pentagon design was considered a much more elevated style of design, because it's harder to do, because you can't pack pentagons in the way that you can pack hexagons and squares, but you can still do designs, really beautiful designs, using the pentagon as your foundation, which we will do in class 5 of Geometry Part 2. Okay, and so here's a much more complicated design here, and you can see how you can work with squares and hexagons together in building this design based in the hexagon. Okay, and here's a more complicated one. We talked about this, how you can find lines in the geometry to make in kind of a three-dimensional way, where you feel like you have ribbons going up and over each other, and these go through boundary areas, often where circles overlap in your original geometric construction. You use them to measure tapes or lines through your design, and you see that very often in tessellation patterns, especially in the Islamic world. Okay, so I want to broaden our thoughts about the tessellation here by using MC Escher. So some people might know MC Escher and his etchings, where he explored figure and figure ground ambiguity, which we've discussed in other classes. And so in these diagrams, like this diagram here, we can see how the black figure of the fields then becomes the ground as you move up for the background of the birds in the sky, and these birds in the sky become the lighter shaded fields in the drawing below. So he plays around with this, and so he's got a tessellation between the white bird and the black bird here. See, you can see the black birds over here and the white birds over here, and they fit almost perfectly into each other, in that they do. And again, you're going from figure of white to and ground of black to figure of black and ground of white. And so what's interesting, especially for us here, is the way Escher actually says he used to work. You know, he would start off with a square or a hexagon, and he'd modify it and modify it and modify it, and then he would get these shapes that he would tessellate together, often where the background and the foreground are different shapes, different animals, often. And so we can see the pattern moving this way. He started with the squares and he's got the white bird, or he started with these black squares and he gets the black bird. And they perfectly tessellate into each other. Okay, and here's another one here where he's working with triangles. He's got white triangles and black triangles, and see how he modifies them until he gets these two shapes, and the birds fly away. Now, why is this interesting? Well, in many ways this is interesting. Oh, here's another one here where he starts off with a hexagon here, right? Using triangles and moving outwards to get these shapes that tessellate with each other. So you've got fish over here, you've got lizards, frogs over here, toads maybe, and you've got birds up here, more black toads and white fish here. So it's figure ground stuff, it's tessellation, and this one's working in the hexagon. This one's working in the triangle. Okay. And here's another one here where we're working. Remember, this is hexagons, not squares, hexagons, because a 3D square is made with a hexagon. And again, if you move from top to bottom, you can see how he creates the tessellation that is not just standard hexagons, it's actually figures that we recognize to represent something like a man. Okay. Now, why is this interesting? Well, it is interesting in terms of the pure geometry and geometric design in illustrations. It's great to read Escher, look at Escher. They're just fascinating. But and it has philosophical implications for Platonism in terms of the same and other and opposite forms. So opposite forms like taller, not shorter, is the opposite to shorter, not taller, is related to the same other that we get in figure, not ground, and where the ground is actually the figure. And then the figure becomes the ground. So you have the opposite forms: taller, not shorter, shorter, not taller, black, not white, white, not black, opposite forms. But it's also interesting to think of this in terms of geology and the structure of crystals. So there's quite a bit of interest in science with these sorts of tessellation or cracking, if you like, that happens on different scales of different geology. So you might be up at the global scale here, and then you might come down to, the airplane scale, or a scale of where you might take a photograph of some tessellation, or you might then go down to the microscopic scale, and you find different patterns at different levels. And these are some recurring sorts of patterns that they tend to find. And one way of understanding them, remember with Escher how, you get the birds or the lizards or whatever, and it's not really clear how he's got to them. Well, he's got to them by starting with hexagons or squares or whatever else. And this is a way of thinking about what they're doing in this science here, where they're looking at the patterns of the cracks and working out exactly what's going on. So one way to analyze is to look and see how many vertices per shape and how many shapes per vertex. So here with hexagons, you've got 3 shapes per vertex, 1, 2, 3. And here when you look in the shape, so the hexagon, you've got 6 vertices per every shape. And so if you work like this, you can see what's going on with cracking in the bottom of a dam during a drought, or tessellated shorelines, or looking at the global scale. Okay, so here's a close-up of the Giant's Causeway here in Northern Ireland, and what you get there is you get lava cooling very slowly, and because it cools very slowly, it expresses its structure, the structure in which it forms into a solid as it slowly cools. And sometimes this structure is to do with the arrangements of the molecules, or sometimes it can come right down to the shape of the molecules itself. So like when water freezes into ice, it actually takes a structure, as we know, that creates takes up more space than how it is with it as a fluid. And so that's why water expands when it freezes. And this is the what we see with crystals as well, where the structure of the crystal at a molecular level can be writ large as the crystal grows in a uniform way, as with these crystals here. So the Giant's Causeway can be amazingly uniform. It's incredible. But you also see this in Tasmania with the dolerite plugs in very old volcanoes, where the plug where the volcano was spewing out lava and then got blocked off, and the lava slowly cools, and you get these columns, and then over thousands, millions of years, the the volcanic dust or the other soils and rocks break away, and then you get these dolerite columns. But you also get tessellated paving in squares here, right? So different structure there in Egelhoopnik in Tasmania. There's another site near Coffs Harbour, I think, that has similar tessellations. So they're all around the world. These are just some examples of this tessellated uh, geometry that expresses in some ways what's going on in the chemistry of the rock. Okay, so that is pretty much it there. So when we're doing all this tessellation stuff, we can hopefully now see how it relates to this chemistry and this geology and the beautiful pictures, curious pictures that, you know, I sometimes just can't stop looking at that MC Escher made so many years ago. Okay, all right, so see you guys in class. This is Platonic Academy of Melbourne, autumn 2025, and this is a video that's made to supplement our Platonic Esoteric Geometry class in part 2.